now, so I make sure I have enough time for the whole presentation. So I'm Samantha McVey, also known on IRC and GitHub and as CMCV, as this says. And my talk's about my work hardening Perl 6's hash implementation against attack. And I'm going to go into some of the details about how these hash attacks work and what they actually target. So Perl people, they love hashes, and when Perl was released, that was before my time, it was a defining feature of the language, and it was one of the big selling points of the language. And it's convenient to use, and Perl is often touted as a rapid development language, and that's exceptionally helpful in doing that kind of rapid development and prototyping. And it's generally fast for computers as well, and especially rolling your own algorithms. It makes everything much easier. And so what are our attackers' goals? I'm primarily looking at denial of service attacks. And so we mostly know about the raw internet traffic, where an attacker just pumps tons of traffic at the server, causing the server to have to spend too much time dealing with the fake requests or just the extra data, and it's unable to serve legitimate users of the site. And so, but hash denial of service attacks don't require very much bandwidth, and they don't require a constant amount of traffic, and it can last until the service is restarted because it pollutes the hash table, causing it to become exceptionally slow. And I'll talk a bit more about that later, but let's go into a real world analogy of how this might work. So we're all familiar with file cabinets, and they're labeled with different indexes. So filing cabinets.
I've got that file folder in my file cabinet.
This exact?
That one.
Okay, so they make looking up documents fast. That's why we use them. We don't just have a stack of papers on our desk and go through every one. That would be insane. And each document is in a folder, and each one is labeled. So this is just by letter, but imagine if it said like taxes or such and such car bill, October 2018 on it. Every folder is going to have hopefully the same tag on it. And so looking up is easy. You choose the right cabinet based on A to Z or so, and you look at the tabs of the folder. There it is. You take it out. Okay, that's what I wanted. That is hopefully how our hash implementation is going to work, and it works similar way. And things should hopefully end up distributed. So, and no two folders. We don't want to name them the same. So how would an attacker exploit our possibly real-world filing system? Well, the attacker knows how you file your papers. They know how you have a predetermined way that you file them and what you label them, and the attacker has figured this out. And so the attacker...
Sorry, we're not getting your video on stream, which is unusual. The mics have just confused your computer, unfortunately. No, everything works fine. Is that better? Sorry about this. That's not fun. No. How in the hell is this happening? It's flipping, literally recording off that. Something's gone slightly through.
Should I just continue?
Yes.
Okay. So the attacker knows how you file things, and they start sending you lots of documents, which, because you have a very rigid filing system, you have to put the same label on every single folder, and then you just end up with a cabinet with the same name. And when you're trying to look up a document, see if it's there, or see the value that it has, let's just say it's on the back of the paper, your notes, maybe you're trying to look up. You can't quickly scan the titles, and you have to compare every document. And this is slow, and this defeats the whole purpose of filing cabinets, and it'd make it much slower than if you just had a stack of papers looking through every one. Because you have to take the folder out, look at it, put it back, take the other one out, etc. And you have to start at the beginning of the folder. So I'm going to now go into computer programming. Now that analogy should help things be a little more understandable. So how do we store data with computers? Well, arrays are pretty simple. In C, that would just mean get me the address that the array is stored in. And you want, in this example, let's say this is a C array. You want to get the second element, so you apply an offset of 1 because of the 0 indexing, and you get that memory address. Very simple. It's basically just addition and lookup. How about hashes? So, a string, and you set the key to the value, and you can also get the value of it. So it almost seems like magic. How does it do it? Well, it's kind of based on these structures. So the array I talked about, and array of references is just an array which links to multiple objects. And so you can have different sized objects, different types of objects. It's more or less rigid. And then here we have a linked list, which allows you to quickly change items and delete and add. So hashes, it's classically an array of references to linked lists. So it's a combination of some of those types and things that end up in the same bucket in the hash table. Here's a little picture. So imagine those buckets are file folders, and we're filing them. And as you add a file, you add something to the linked list. Does that sort of make sense for people? Okay. Yeah, in the file system analogy, I will discuss that. So let's go forward. Okay, so in a lot of these attacks, so usually lookup and insertion is a 1 average time, assuming your chains don't get too long. And the attacks take advantage of the properties of data structure. So the attacker would basically make, like the files folder example, make all the file folders have the same name, and you'd get these very long chains, and it would defeat your entire use of using hashes and make it slower than an array. And so I'm going to go over some of the smaller attacks. We are able to compare like the labels of the file folder, and then we have to compare every single one. Yeah, so hash function is similar to an array, and that linked list you see here. So how do we know which bucket to put it in? Well, we use a hashing function to turn this data into an integer, and basically that takes an arbitrary string of data, turns it into a number, and then we use the remainder of that number depending on the number of buckets. So if we get the number 9, remainder 8, that's 1. So then we'd put it in this bucket here, etc. Or we can use a bitwise AND operation, which achieves basically the same result. So similar to how everyone probably knows MD5 sums, you take a file, MD5 sum, you get a number. It's meant to be faster than that because you want hash tables to be as fast as possible. Otherwise, you just use an array if you want that to be fast. So let's talk about how we turn a string into a number. Let's just take the simplest hashing method you could come up with. Just add up all the code points in the string, and you get a number. And it's obviously terrible, and you can think of for a second why this might be bad for security. And let me see. I'll skip that slide for a second. So here you can very easily reverse it. So you can add them, and then you can also go backwards and subtract. And so if you have the addition is easily reversible, and that's one of the reasons I just went to the cheapest and easiest hash function, is because it makes it easier to conceptualize how the meet in the middle attack works, which is a very severe attack on the hashing algorithm itself. And so it exploits a weakness when you're doing multiple rounds. And so in this example, each round is each code point in the string. So that's because each round, each adding of the processing of each code point is identical. So you're really, if you imagine it as an encryption operation, it's basically playing the same operation multiple times, and each letter is the data. So because of that, you can reverse it, and I'll explain that a little more. Okay, so this goes off the page a little, but that is essentially just these numbers plugged into this function. So you have the encrypt A alpha is same as encrypt beta, and for the string foo bar, string A is foo, string B is bar, because we're doing the exact same operation each time, and it's reversible. So this makes it so we can then reverse it by taking the hash value here, plugging it in, getting back 324, and then we can essentially because you get it, you know the target string foo bar. We know the target is 633, and so the attacker knows. The attacker knows at 633, and they're trying to conflict with the string foo bar, which let's say is in a critical piece of your infrastructure, a hash that's used all the time during lookups of web requests. And so you want to pollute it so it conflicts with bar and it slows down any request that accesses the bar variable. So what the attacker does is they do the forward hash. Let me go forward a sec. Okay, so you generate a dictionary of random strings, and so you're trying to find a way to go backwards. So first you go backwards using tons of random strings from 63, and you store it in a dictionary, and then you're able to combine the big dictionary of half of the way with another random string, and it allows you to reduce the complexity. So essentially, I may have it on another slide, but I will give you a demo in a short bit, and you'll be able to see how very fast it is. Okay, so yeah, here let's say content type, a common HTTP header, has the hash code 1194, and so this is a Perl pseudocode attack, which would work against this and often other functions, and I'll give you a second to read it. And it's, aside from not defining backhash function and forward hash function, this is essentially how the demo I'm going to give in a bit works, although it's written in C. So you create the dictionary here, and you have your target. And so you create a random string. So we're making a large dictionary. We just create a random string of 3 code points. We put it in the backwards hash function, which in our previous case is subtracting each one from the end. And then we get the backward hash, which is basically we find the middle value of these possible random strings. So we're trying to generate a dictionary that allows us to make it easier to find a middle point. We want to find a middle point that we can then attack instead of trying to solve for the entire string. So we generate this dictionary, which is much faster than doing a brute force, and only has to be done once. And then when we want to crack it, we just start adding random code points to it and hashing it forwards. And if the two meet in the middle, we found a conflict. So we take the dictionary, that's generated once, generally pretty fast, and then we take that string and we find if the values meet in the middle, then we have a conflict. So here we go. Okay, so this is a function that used to be used in Java, DJB33 hash. I'm not sure if it's still used in Java. It may still be. I believe Java's response may have been put your own hash function in, and they weren't going to change back compatibility, though I'm not 100% sure. Don't quote me on that. And so this, you can also put backwards more common operations to reverse. And in this, you multiply by this number, because this is just always true. I don't have time to fully get into it, but just take for granted that this works, and that is the backward sequence like subtraction was. At least for 32-bit integers, this is the reverse operation of that.
I think that's the one we used in Perl 1.
Ah. Okay, and now for the demo, which is going to be pretty fast. So this is the DJB33, and I'm using a meet in the middle attack that I wrote myself, and it stops after a certain number, and content type is the target string. I could have put any string in here in my file I wanted, and this is how fast it is. And so that, yes, with content type, and those generated right now. It's very fast. And there's a slight pause at the beginning as it, you may not see it, when it generates the dictionary, which is the slowest operation. And then past that, you already have a huge dictionary and a high likelihood you'll get a conflict because you're simplifying the operation. So, can we do this in MoarVM? So in case you don't know, MoarVM's the virtual machine that Perl 6 uses, and I'm a developer for MoarVM as well as for Kudo Perl 6. So I wanted to find out, can we do this in MoarVM? And so this is the function that we use. It's Jenkins hash, and you essentially just add the code points to 3 different variables, and then you mix them together, and you do that for the whole length of the string. And this is not super important to understanding, but I put it on the slide for reference. And so this is HashGenMix, by the way. It's quite a lot of mixing between the 3 variables. And so it seems complicated, though it's even more trivial than DJB33 traverse. But unlike DJB33, which has 1 state variable, we have 3. So even though you can reverse it, you then have 3 values that you have to meet in the middle for, and they're all 32-bit integers. And that I did write a program, but I didn't get anything in 20 minutes compared to the other one, which generates things quite quickly. So I decided that this is probably not the proper exploit for it, which is good. But I mean, we can do better than that, hopefully. And so how did Perl 5 solve this issue? I'm going to talk about that for a bit. So Perl adds a secret suffix to the end of strings. And so instead of changing their hash function, which may have made it slower, oh, for sure would have made it slower, they added a secret suffix to the end, which defeats the meet in the middle attack, because then the attacker is not able to meet in the middle for a string that it doesn't have. And it increases mixing for short strings, because there's the issue where for short strings, the attacker would be able to exploit it because it only got mixed a small number of times, and it could, with an attacker probing, it could possibly reveal more information about the hash secret, which is mixed in early in the phase. Not enough mixing going on there. And it helps prevent multi-collisions. And so what are multi-collisions? So this is, I guess, the second worst attack I'm going to talk about, probably generally as far as hash algorithms go. A multi-collision occurs when you can generate a string which gets a conflict no matter what the hash secret is. So the hash secret essentially is supposed to make it so the attacker doesn't know how you file your folders. You have a hash secret, and let's say on Tuesday it's this. So essentially when you start up the program, it's different. And so every time your Perl program starts up, the hashing order is going to be different. So in this case, the attacker doesn't know how you file it, and so therefore you're hoping they're not going to be able to figure out, I'm good to go. But if you have a multi-collision, then you're totally screwed, because then it doesn't matter what your hash secret is, it collides no matter what. And so this was broken for Murmur Hash 2, Murmur Hash 3, City Hash 64, likely others, and Ruby and Python were affected. And so it's been proven that because of this, Python's hash secret could be found quite or actually not because of this. I believe it was some other reason that could be revealed. And so what do we want from a hash function? So it shouldn't be vulnerable to meet in the middle. And hopefully it's still fast. So as you saw before, I stated how the MoarVM's hash function, even though it was easy to reverse, it had so many state variables that it was not effective to try and find the exact same three 32-bit values once you have that dictionary. So most of the more secure functions, such as ziphash, which Python 3 and Ruby now use, the people who created ziphash, they were researchers that started studying these hash functions because they had never been studied too much before. At least what I've read online is that academics often dislike hash functions because they're imperfect and they're not as nice mathematically as a non-one-way function or a non-two-way function and not proper encryption. So they were able to break most of the popular hashing functions. And so they decided, okay, we'll write our own function that will be secure. And so cons, it is slower, and it's not a magic bullet. It doesn't fix other issues in the hash table implementation. It just affects the hashing algorithm. So it does fix that, and the pros is it's well researched, and it has very good distribution, even for short strings. And so let's talk a bit about a different issue, bucket determination, which basically, so you have the number that you get from the string, and now that you have that number, which filing cabinet, which bucket do you put that in? So we talked about you can use modulo with the number of buckets, or you can use bitwise AND. But what's wrong with this? It only causes the lowest bits of the hash to actually be in effect. So if you have 8 buckets, then you're just going to have the last couple bits be active, because when you do let's say if you AND it, that's the only bits that are going to be ANDed essentially. So it wastes all the entropy. Let's say you have a 64-bit, 32-bit hash, you're only using 12 bits max, or maybe 8, depending on the size of your table. And so the attacker doesn't need to generate conflicts for your whole hash value. They only have to care about 10 bits. And so that makes it much easier, and makes it easier to attack 64, 32-bit hashes. So how can we let's look at a graph. So black, which there's no black here, but blue is a 100% chance of the hash value changing. So the columns are each of the 64 bits and the input hash value. And the first 2 columns are the output bits for table size 4. So essentially, this is a hash table size 4, this is 8, 16, etc. And these are each of the 64 bits in the final hash value. And essentially, we're trying to find out if we change one of the bits in the 64-bit hash, what's the chance it's going to change which bucket we put it in? And so this is pretty terrible. There's essentially only 1 bit that changes per size at a certain location, which causes it to change buckets. So that's the standard modulus. So I'm going to talk about Fibonacci hashing. So Fibonacci hashing is a variant of multiplicative hashing, which was originally developed instead of real hashing, where someone would say, I want to hash a number. Back in the old days, you have a number, you want to put it in a hash table. Let's just multiply it by a very large number. And then it'll loop over, and we'll take the remainder, and it'd be good. I mean, it's better than doing nothing. But in this case, the golden ratio, it's how plants, they will grow the first leaf here, and how do they know where to grow the second leaf? Because they don't want any of the leaves to overlap as they grow, because that wastes sunlight. So you can see here that essentially none of them overlap, and even if they have an infinite number of leaves, none will be in exactly the same spot, and it'll never become basically the same sequence repeated. So that would be 360 degrees over phi. And so phi is the most irrational number. And so instead of dividing, actually here, the sunflower seeds, this is using the golden angle. This is the golden angle plus 1 degree. This is the golden angle minus -1 degrees. So you can see how it's quite specific about what it is. So here, how does it look when we multiply by essentially the highest 32-bit integer divided by phi is what we multiply by. So here, this is with Fibonacci hashing and multiplying the hash value by this very large number, which then wraps around a bit. So when the additional benefits, when the bucket's full and the hash table expands, you're now rotated a bit. And so if, let's say by chance you're getting some conflicts, when the table expands because it's starting to get full or the bucket gets too long, then assuming it's just standard operation, they're less likely to end up in the same bucket, which is helpful. And as you can see, this is much, much better than the other one. It's actually, it's not totally perfect, but you have 64 bits, and that's good enough. Yes, and so we don't have to rehash during the normal course of usage, because let's say we are only using 10 bits of our hash, and we get some conflicts, and things are not going our way. Let's say it's not just an attack, it's just our data set. There's something going on. And I believe Perl 5 has a rehash where it rehashes things. Yes, that too. This avoids having to rehash because it's using more bits. So there's more bits that can change the output. And it makes brute forcing more expensive because they can't just factor in a short number of bits. They have to factor in essentially most of the bits. And the only practical downside is if your hash values are Fibonacci numbers, then you'll have bad distribution. But given that we're using a hashing algorithm, that is not really too much of an issue because they're not very much in a 32-bit number. A very small fraction are Fibonacci numbers. And so the hash secret may be the most important feature that I'm discussing here. So without it, essentially, maybe it was 2001 that Perl 5 did this, 2002, that they randomized.
Because I remember where I was working at the time. It was late 2003. 581 tried it first with the Arco, and that had problems. 582 introduced the rehashing, which solved the initial set of problems, and then he figured out how you could exploit the rehashing mechanism about 6 or 7 years later, and then we removed it and went for full randomization, which we should have done much earlier.
Yeah, well, I know we didn't do it in 5.6, but that's the one I watched.
Okay, so after 5.6.
581 and 582 were the two goes of doing it. And that
Okay. So this is very important because otherwise all Perl instances are all going to have the same filing system method. And so even you could have the strongest hashing function and the best way of determining where the bucket goes, but if all the Perl implementations all have the same way of filing, brute force becomes very, very attractive. Yes?
I think mathematically the hash secret is the equivalent to having a secret prefix that you hash each time. So like you said about secret
Yeah,
prefix, you can have
yes.
a secret set, the same secret set of things you've got at the beginning. So you could think of it that way.
Yeah.
Easy to understand.
Yes, the hash secret, yeah.
Sorry to interrupt.
Okay, yeah. So that is true, basically. The hash secret, instead of, let's say, as I said, Perl 5 adds a secret string to the end of the string to be hashed to randomize it, the hash secret is similar to having a prefix. I mean, it's not mathematically identical, but it's essentially what it achieves. though the difference between the suffixes are stronger, though you do need both, because with the hash secret, that's a single starting state. And though hopefully you would have both if you have a hash function which could be possibly vulnerable. So as I said, if you don't have the randomization, then you could spend CPU, let's say you take 2 days of CPU, maybe in 2 weeks. Okay, you took 2 weeks of CPU time, but now you can attack every single Perl instance all over the world. So doing the secret randomization, very effective, at least in making the attacker actually have to do attacks based on each server individually. And so basically everyone implements some degree of randomization, and often SIP hash is used because of it being more proven and tested against attack. And so Ruby switched, Python 3 switched, and as I said before, Perl 5 didn't switch the hash functions, but did those other things to protect itself. Let's see, have a little bit of time. So let me talk about iteration order. And as you all know, Perl 5, you add a hash key, and then your hash order is totally different. If you have tried that, once you add a key, everything will have seemingly switched around. And so the iteration order, it can reveal information about essentially how it's laid out in memory. You want to try, either you want the attacker to only have access to, let's say, the insertion order. So Python 3 now, the insertion order is guaranteed, and it's not random. So you either want the, because the attacker already knows the order they're inserting keys, and they gain no information if you retain the insertion order when you're iterating hash, or you can also not retain the order, but then you have to randomize it. So there are those are basically the two choices for not revealing how it's laid out in memory. And so this can potentially be used to attempt to find the hash secret or create collisions within the bucket, because then you know which keys are next to each other. When you iterate, you can add a key. The attacker requests the information. Okay, these two are next to each other. They're probably in the same bucket. They add more, they find out more information about how it's laid out in memory. And so Perl 5, it randomizes the insertion of keys in a bucket. So it either places it first, in the file cabinet example, you put it in the first file item, or let's say behind the first thing. And so it may not seem that random on its face, but once you add, let's say you add 100 items in, and you're randomly adding as the first or the second item, it is not perfectly shuffled, but more than you might think. And as well, it randomizes the order that the buckets are iterated. So you have that randomization within the between the buckets and randomization of the bucket order. And Perl 5 uses a linked list similar to MoarVM. I mentioned a bit before, Python 3.5 did reveal the order of the structure, and then 3.6 on, they just had things retained in insertion order. So that seemed more based on people using Python liked the insertion order, and they didn't want to use the ordered map. They wanted it all just to be ordered. And so it's now guaranteed from 3.7 on, and it stores things in a type of sparse array. So Ruby also decided, past 1.9, it retains assertion order, and they use a circular linked list. Okay, so Perl 6 on MoarVM, I believe SIPhash has been merged now, and this slide is a little old, but I randomized the insertion order a couple months ago, and the insertion order, which luckily the Perl 5 code was somewhat helpful for me in looking at that. And so we've randomized the hash secret as of 3-4 months ago. So what are issues with linked lists? Because we talked about all these attacks and issues. They attack certain components of our algorithm, the hashing implementation, not revealing the order in the memory, trying to make sure that our hash value, all the bits are used, etc. So linked lists, they can still degrade in normal usage when entries leave the cache. They're more vulnerable to hash flooding attacks, which aren't the denial of service attack I talked about, but basically just putting tons of things in it. And you have to do new allocations when you expand the table or add new items, and that takes time, causes memory pressure with the garbage collection as well. Let's see, it's not quite ideal, but it is fairly simple to program, at least as a programmer programming in C. Though in the future, we may want to move to an open addressing type solution. At the same time, it would make the hashes more memory efficient because instead of having to store an array of references to the hash entries, they would be stored inside the table itself, allowing to fit better inside the cache. And so the takeaway, even if your algorithm is fast, if your inputs are user supplied, you have to assume the worst. This is just a little summary about hash randomization, attacks against the function itself. You want to make sure the function is reasonably secure. You want to make sure to use the whole range of the hash value, because why are you generating 64 bits if you're not going to use them? And 64-bit hashes reduce likelihood of collisions, though they don't help with collisions in the same bucket, and you're hopefully using the whole value to determine the hash bucket to try and mitigate that. And so let's go with questions. We have a few minutes left. Yes? Can you speak up a bit?
Sorry, I happened to be looking at it, and Perl 528 has apparently replaced the zip hash.
528 replace zip hash?
Yeah, I'm not sure if there's apparently something called Zaphon hashing or something like that.
I'm not aware of that, though I do believe Perl 5, it's been a command. It was more of a statement question. He mentioned that 5.28 Perl has removed zip hash, and I was commenting that I believe zip hash has always been optional when you compile and not the default. It's possible they removed it as an option. I'm not sure about that, so that's interesting information. I'll have to look into that. Anyone else? Yes?
Is the multi-hash attack actually named after the multipath?
No, it is not. Yes, if the multi-hash was named after the multipath, and no, it's not. Yes?
Yeah. So it's going to be a repeat something from in Perl 5, the API provided allows you to pre-compute hash values. The implication of this is that there can only be one hash secret, the thing equivalent to prefix, across the entire process. In MoarVM, are you using one secret across the entire process or one secret per hash?
Well, okay. Okay, so we do have one hash secret,
Yeah.
though okay, the question is if there is a hash secret per hash or a hash secret per process. And so there is a hash secret per process on MoarVM, though there is a bit of randomized data attached to each hash, which determines the iteration order. But we to our string types, we can store the hash value cached. So if you use it in other hash tables, you don't have to compute it again. So we would have to rework so many things to change that.
So effectively, that's why it's one per process, because it's kind of the same thing as Perl 5. The hashing information is shared between hashes to say it's you.
Yeah.
Okay, thanks.
Yeah. And yes, it's the linked list. Well, you randomize if you insert it as the first item or the second. So if there's nothing in it, you just put in. But if there's already one or more entries, you randomly decide to insert it ahead of that or after it. And so eventually things will just end up getting shuffled. Any other questions? Yeah.
Follow-up, I was mistaken. Additional hash functions were added.
Okay, so the
Still there.
he said that SIPhash is still there, but the new hashing function, what was it called? Zaphod 32 has been added as well, and I'll have to look into that after the talk. Any other questions?
You mentioned a couple of times that this was for string keys. What happens when that's not the case? Like, do we have keys that are not strings, and what happens then?
Okay, we have keys that are not strings. Okay, the question was how it works for keys that are not strings. So Perl 6 also has keys that aren't strings. You can use objects, though it is a bit of a hack onto the string implementation. So it essentially does a little hack on it, and so basically it's the same.
Quite an extensive hack, actually. It's all based on the fact that every object in POS6 has a .which method that you should give them unique identification.
Liz has mentioned that the hashing of objects, it uses the .which method, which is which identifies the object, what it is, and it has to use that when you hash objects, and so that incurs a little penalty because it has to go into the object interface to figure out what it is. Anything else? Okay, great.